Hi, this is Laura Sliminski with Edina High School. Today we're doing lesson 14, solving logarithmic equations. In this lesson, I'll really put together everything we've done this chapter. The first thing we have to be able to do for this unit is to be able to take a log and convert it to exponential form, which is something we've worked on. So I'm just going to do a couple of these with you. As we remember, we said when we see logs, we read it as the what power function. Since there's no base, it's like a base 10. So I'd read it as what power of 10, so I write this, what power of 10 is 10,000. So that's kind of how we started this chapter, and then we realized that the answer was 4, so that's the exponent. So that's a reminder of how you go from log form to exponential form. The base of the log goes here, the answer is the exponent, and then what you're taking the log of is what it's equal to. So for example, letter B, there's no base, so it's 10 to the 1/2 power equals the square root of 10. And finally, log base 2 of 256 equals 8. I could rewrite it as 2 to the 8 equals 256. So this was just a reminder of how to convert. But now if we go down to questions E and F, just a reminder, ln is the natural log. And we learned before that that is log base E. So if I want to write a natural log and exponential, the base is e to 0 power equals 1. So we'll use that later today. Now ultimately, the concept for today is solving a problem like f for the x. So our goal for today is to be able to solve logs when we're taking the log of a variable. And the reason this warm-up reviews the skill of converting to exponential is because that's the strategy we need. Once we have a log equal to a number, if we convert it to exponential form, let's see what happens. So the base here is 10. So it'd be 10 to the third equals x plus 2. So while the log was there, I wouldn't know what to do to solve for the x. But you can see if I convert it to exponential, now I know 10 cubed is 1,000 equals x plus 2. I can subtract 2 from both sides. And I get 998 equals x. This right here is really the concept for today's lesson. And the rest is just understanding that we are also going to have to be able to apply our properties of logs that we've been learning throughout and do some more difficult algebra than this. But the idea is just to be able to solve for a log when it's a log of a variable, and we do that by converting to exponential. So for example, if we look at this next example, we have log 3x plus 7. It says solve. It tells you to write it as exponential and then solve for x. So I would take base 10 to the 0 power equals 3x plus 7. 10, anything to the 0 power is 1. And then again, we just solve algebraically for that x. Now, because we learned throughout this chapter that there's restrictions on what we can take logs of. Okay, we learned that we can't take the log of 0 and we can't take the log of any negatives. When we solve for logs, we actually have to pay attention to extraneous solutions again. And we've seen that before. And really what you're checking for is any logs that you have in the problem. Okay, so no matter what the base is, whatever you're taking the log of, that has to be greater than 0. Because, we can't take the log of 0, we can't take the log of a negative. So really, in this problem, for example, I need to take what we're taking the log of the 3x plus 7 and make sure that when I plug negative 2 in for that I actually still get a positive number. So you could take what's inside the parentheses, 3 times negative 2 plus 7, negative 6 plus 7, I get 1, that is greater than 0. So that is an answer. If my answer was 0 or less than 0, I would call it an extraneous solution. I would pause this now and take a few minutes to try number 2 and then check your answer. When I did it, I wrote it in exponential form. 2 to the 4th equals x plus 5. 2 to the 4th equals 16. Subtract 5, I get x equals 11. And again, I don't always show my work like I did up here, but if I put 11 in, I get a positive number, so that's okay. So those are the most basic type questions that you will have. And again, the rest of the examples just keep adding layers and show some different twists and turns. For example, number 3, this one has 2 logs on the left-hand side. Like I said, we can't write it in exponential form till we have a single log equal to a number, so now we have to apply our properties of logs. And if I have 2 logs times each other, we've done a lot of skill work where I can combine them as a single log by taking one log of those two things times each other. When I rewrite this in exponential form, I get 10 to the first equals x plus 2 times x plus 5. And now, again, it comes down to algebra. I get 10 equals, I FOIL these out, or you could use the box model to multiply, but you should get x squared plus 7x plus 10. Now, we have a quadratic, so it reviews the skills of solving quadratics. To solve a quadratic first, it always has to be equal to 0. So I subtract 10 from both sides. These 10s cancel out as well. So now I'm left with a quadratic still, and I always look for greatest common factor because we will think about solving by factoring. Well, they both have an x in common. So nicely in this one, when I factor out the GCF, now I'm left with the factors. And we learned earlier this year that once it's in factor form, you would set each factor equal to 0 and solve for x. So in this case, I start with the options of 0 and negative 7. Again, what I was taking the logs of were x plus 2 and x plus 5. So I do have to check if I plug 0 in here. Yes, that's greater than 0. So that's okay if I plug 0 in here. Greater than 0. So x equals 0 is an answer. Take negative 7, and if I put that in for the first log, I get something less than 0. So that does not work. So this one would be an extraneous solution. So this is our first example of how we would need to use our log properties, and also of how we would get an extraneous solution. Now the next exercise talks about how Drew was given the problem of log base 2 of x plus 1 to the 4th equals 8. And so when he got that, he decided to write it in exponential form and expand out the x plus 1 to the 4th. When he did that, he got this big ugly thing and realized that he wasn't able to solve it. So he thought it could be solved. And they're just asking us to say, is that actually true? And I like this problem because it reinforces the idea that we have to remember we have other properties of logs. He wasn't incorrect to expand it, but if he did, he got stumped. If you ever start a problem and you get stumped, go back to the beginning and think about if you had a different strategy you could have used. And in fact, we learned a property where if we have an exponent, we can always move that exponent to the front. If we do that, it simplifies this problem. Now I have 4 times log base 2. My next step would be to divide by 4. I get log base 2 of x plus 1 equals 2. And now it's like a problem on the previous page where we can rewrite it in exponential. I get 4 equals x plus 1. Subtract 1, I get x equals 3. If I plug that back in, 3 plus 1 is positive, so I can in fact solve this. So this exercise really shows the importance of understanding your properties. And even if you make a mistake sometimes, again, it wouldn't have been incorrect for you to expand it out, but you could get to a point where it's stumped. So the next few problems just reinforce this. Again, I would recommend pausing it, and trying it, and then checking. Okay, so in this case, you should have changed it to 5 natural log 4x equals 15. Anytime you move that in front, then divide by it. Sorry, that's a 5. Natural log of 4x equals 3. Again, in the warm-up, we talked about if it's a natural log, it's an e to the 3 equals 4x. Divide by 4. Now, if you get an e in your answer, you can just leave it. We did learn that it's a positive 2.7, ... goes on forever. Having said that, it's a positive number divided by a positive, which makes it positive. If I plug it in here, it's still positive, so it is a solution. Next one, again, I would move that 2 to the front. 2 log of 2x plus 5 equals 4, divide by 2. I'm doing these quickly just because you should have already done them. And we're just checking our work. Again, it's a regular common log, so 10 squared equals 2x plus 5. 100 equals 2x plus 5. I'm going to subtract 5 from both sides. I get 95 equals 2x. Divide by 2. So it is okay to get fractions or decimals. I get 95 over 2. And if I plug that in, I would end up with a positive. So that is okay. Alright, the next one was just a good example of there would be no way you'd want to expand it 19 times like the exponent. So once again, you'd move it to the front, do one step here, and then divide by it. Okay, so I took kind of the shortcut here. Hopefully you have the idea by now. Equals 3, and I get 2 to the 3rd equals 5x plus 7. I'm not going to show my algebra on this, but when you did it, you should have gotten x equals 1/5, which did work. Alright, number 5, we're just going to skip over. we'll do another one similar to it where it's a subtraction instead, but the algebra I'm not going to worry about right now. Okay, number 6, again, I would pause it and try it to see if you're getting the idea, and then come back. There's multiple ways you could have done this, but I see it and I just changed it to log of 3x times 4 equals 4. Log base 2 of 12x then equals 4. Okay, so 2 to the 4th equals 12x. 16 equals 12x divided by 12. And if you do have a fraction, make sure you reduce it 4/3. Put it in. That gives me a positive. We're good. I do just want to take 1 minute to talk about how you could have recognized something else and done this differently. This is a good example to show that there's not always just one set way to approach a problem. I recognized that log base 204 is actually, I can evaluate that because I'd ask myself what power of 2 is 4, and that answer is just 2. Okay, so sometimes you're able to actually get 2 paths to solve the problem. In this case, I would subtract the 2 from both sides. I'm left with log base 2 of 3x equals 2. And now I have 2 squared equals 3x. Divide by 3, I get x equals 4/3. So you see I get the same thing both ways. And both will get me to where I want to go. I'm just going to do one more with you here. It shows just a couple more concepts and then, well, maybe 2 more. Having said that, number 7, we talked about already this chapter. If we have 2 logs that we want to combine as 1, we can't apply our properties as long as this 2 is out front. So you do, in fact, have to move that to the exponent. So I changed it to the natural log of x plus 2 squared. Minus natural log of negative x equals 0. Now we have an example of subtraction, and I combine those by division. X plus 2 squared over negative x equals 0. In this case, I would rewrite it in exponential. E to the 0 equals x plus 2 squared over negative x. It would be 1 equals x plus 2 squared over negative x. Now I don't like the fraction, so I'm going to get rid of it. If we have a fraction, we can always multiply by the denominator, and I can do that because I'm going to do it to both sides, and it moves that denominator over. So I get to the point where I get negative x equals x plus 2 squared. So this has a lot of algebra in it. X plus 2 squared is the same as x plus 2 times x plus 2. Common mistake here is that when people multiply that out, they'd actually get x squared plus 4, just plus 4, and they miss this middle term. Be careful with that. Add an x to both sides. Because I have a quadratic, I need it equal to 0. And now this is a good reminder of sometimes we have a quadratic. We check for the greatest common factor. There isn't one. Now I use the x box method. So in my box, I have x squared and 4. 4x squared, 5x. 2 things that multiply to get the top, add to get the bottom. 4x, 1x. And then I pull out my GCFs of every row and every column. So I get 0 equals x plus 1 times x plus 4. Set each factor equal to 0, I get x equals negative 1, x equals negative 4. But when I plug in a negative 4, that one's extraneous. So I'm going to stop there. Negative 1 did work. One other concept came up, but you can take a look at that. In the last one, you have logs on both sides, so you'd want to just make sure you use your properties. 12 over x plus 3. And if you have a single log on both sides, you can virtually ignore the logs. Okay, so in this one, when you went to solve it, that's how you would set it up. All right, your homework was numbers 1, parts A, B, C, D, part 2, A, and number 4 is A through K. Thank you.